Today I'll be presenting our work building a system to support large-scale data analytics. This is joint work with Thomas, Jitu, Carlo, and George at Microsoft, and my advisor, Brighten. Large organizations process massive volumes of data. Reports from several organizations indicate that they collect up to hundreds of terabytes of business-critical data each day. The data can arise from, say, logging user activity, collecting click logs and request logs, or monitoring remote infrastructures to collect telemetry information. This data arises in a geographically distributed manner across data centers around the world because we want low latency for our end users. So now we have this large volumes of data being collected across several data centers, and now we want to jointly analyze all of this data. A particularly common paradigm is SQL analytics. In all the organizations that I just mentioned, a critical component of their analytics pipelines involves running SQL queries to extract useful insight out of all of this originally geographically dispersed data. And how is this supported today? Well, the typical solution is to simply copy all the data to one central location, one central data center, where all the queries are then processed locally, meaning the entire analytics process is centralized. But this centralized approach is problematic for various reasons. First, it consumes a lot of bandwidth. And several recent studies indicate that the cost of the external network is the fastest rising component of data center costs, that internet capacity growth is unable to keep up with this rising demand, and that we're already at an unfortunate point where we have individual data centers whose internal bisection bandwidth is an order of magnitude larger than the total capacity of the entire internet. And in addition to these bandwidth concerns, another kind of difficulty is sovereignty constraints. Many countries are thinking about laws that would stop sensitive data about their citizens from leaving the country's borders. Now, if multiple countries place restrictions on how far the data can be moved, there may not even be a single central location to which you are legally allowed to copy all of your data. But our speculation is that even if copying raw data outside is not allowed, copying derived information, such as reports and aggregates, might still be acceptable. So a combination of factors is rendering the centralized analytics approach increasingly unsustainable. Instead, we have been working on building a system to support geo-distributed SQL execution. Our system takes SQL queries and decomposes them, executing them in a distributed way across data centers. For a simple example of how this would work in practice, suppose we have two data sources, an ad serving log and a click log, partitioned across n data centers. And now suppose we're given this SQL query to process, which first pre-processes the two data sources and then joins them. A join is a relational operation which essentially merges data streams by looking for matching entries in them. And then you run a machine learning computation to cluster the join output. The centralized approach would simply replicate all the data to one data center where the entire query would then be processed locally. And let's say this requires 10 terabytes of data transfer each day. But suppose instead you were to do this. Suppose you were to push down the pre-processing computation to the individual data centers holding partitions of the data, then run a distributed semi-join, which is a standard distributed join algorithm from the databases literature in order to process the join, then centralize the join output in order to compute the k-means. We found that this would only require 30 gigabytes of data transfer each day, which is a 330x cost reduction compared to the centralized approach. And as we'll see later, this level of improvement is typical of what we find in realistic experimental workloads. In addition to supporting basic distributed execution, our system also incorporates several optimizations, including adaptations of ideas from distributed and parallel databases and the distributed systems literature, and we also introduce several novel techniques of our own. The common thread is that all of our ideas are inspired by revisiting classical database problems, such as query planning and view maintenance, from a networking perspective. And as we'll see soon, this leads to interesting design outcomes. So now, let me start by defining the problem that we're trying to solve carefully. First, When you build a large-scale execution framework like ours, there is a range of requirements that we can choose to target: bandwidth, sovereignty, latency, consistency, fault tolerance. While all of these are valid requirements, we chose to focus on the subset of these that would be appropriate to the kinds of batch analytics that is dominant in large organizations today, where you want to minimize bandwidth cost and you have sovereignty and fault tolerance constraints to meet, but because what you're doing is batch analytics, the latency of analytics execution is not that important, and many times you can get away with relatively simpler eventual consistency models. Our system aims to minimize bandwidth cost while handling sovereignty and fault tolerance constraints. Next, in addition to targeting support for the full-fledged relational model, there are 4 other key characteristics which essentially define a problem setting. Second, we have no control over how data is partitioned. The choice of which piece of data goes to which data center is dictated by external factors. Typically, the latency observed by the end user who was originating the data in the first place. So we have to deal with the data partitioning that is given to us. Although we can and do replicate data to other data centers if that would end up improving performance. Third, because each node in our topology is actually a giant data center with a practically infinite amount of cheap CPU storage and other internal resources, cross-data center bandwidth is by far the most expensive resource in our setting, and it is the resource we exclusively target minimizing. And finally, the bulk of the load in our system comes from a stable, well-defined recurring workload. This is something we've seen in production logs at various organizations. Most of the load on the analytics pipeline comes from, say, 20 or 30 fixed queries that are run every day. And this is a massive advantage for optimization because we don't have to hedge the system against whatever arbitrary workload might be thrown at us at some point in the future. Instead, we can precisely tune the system for the exact workload that we know we're going to observe. So putting all of this together, this is the problem statement we are faced with. We're given data that is being born, distributed across data centers in a certain way, and now we want to run SQL queries, complex analytical SQL queries across this data. The aim is to minimize bandwidth cost while handling sovereignty and fault tolerance constraints. The system will be able to handle running arbitrary queries at runtime, but it will be configured to optimize a specified, stable, recurring workload, which is assumed to make up the bulk of the load in the system. Now let's see how we solve this problem. This is the basic architecture of our system. Data enters the system from end users at various data centers, and at each data center, the data is cleaned up and loaded into a local single data center SQL analytics stack. In our current implementation, this is Apache Hive. Then the reporting pipeline, or whatever else is giving us queries to execute, submits these queries to a central coordinator, which orchestrates distributed execution and returns the final results back in the pipeline. This is the basic skeleton of the architecture. But we also incorporate several optimizations over this basic architecture. The optimizations can be divided into 3 layers, depending on the semantic level at which they operate. We have a more or less computation-agnostic runtime data transfer optimization, a workload planner that operates based on an understanding of SQL semantics, and highly targeted optimizations for specific kinds of functions, such as percentile and .k optimizations. Today, I'll be discussing this optimization stack bottom up. We start with the runtime optimization. This is an almost physical data transfer optimization we implement that works irrespective of the nature of the computation passed into the system. And it takes advantage of the fact that in our setting, CPU and storage within data centers is cheap, while bandwidth between data centers is the expensive resource. So we trade off CPU and storage to achieve a bandwidth reduction by using caching. We aggressively cache all intermediate output produced during query execution. Suppose we have 2 data centers A and B, and at time equals 0, B asks A for the result of running subquery Q. Then A computes the results Q0 and sends them over the network to B. After the computation completes, both data centers store a copy of Q0 in a local cache. Now suppose sometime later, at t equals 1, B asks A for the result of running the same subquery Q again. Then we recompute the results. A recomputes the results to get Q1. but it only sends over the diff between the new results Q1 and the old results Q0, thereby achieving a data transfer reduction. And B would apply the diff as a patch onto its copy of Q0 to reconstruct Q1. Now, one thing to note is that we're still recomputing Q1 from scratch each time a day, meaning we're not using caching to save on latency or on CPU. If anything, in most cases, we end up worsening the CPU and storage use within data centers by storing these cache results, computing diffs, and applying patches. But what we do save on is bandwidth, which is the only thing we care about. And again, we cache all intermediate output, which means that caching helps us not only when the same query arrives repeatedly. For example, this can happen in the kinds of sliding window computations we saw in the preceding talk, but also when you have two different queries that share the same common sub-operation. That is, this mechanism gives us automated cross-query redundancy elimination. And for those of you familiar with databases, in this way, the kind of caching we do is almost an automated mechanical form of view maintenance and materialization, with the advantage that it works for arbitrary computations. The disadvantage is that compared to relational view maintenance techniques, this uses more CPU and storage and can sometimes miss opportunities for optimizations that those techniques would otherwise have got. Now let's move one level up to the SQL level workload planning. Remember we said we'd be optimizing the system for a specified stable workload? Well, we have this workload and a bunch of sovereignty and fault tolerance constraints, and now we have various decisions we need to make. Query planning, task scheduling, data replication. The challenge we're faced with is that the optimization space is immense. The number of possible choices is exponential in the number of data centers, the size of the workload, and the complexity of the workload, and it gets very unmanageable very quickly. So the approach we take is to simplify the search space by taking advantage of a particular feature of the relational setting. To understand this simplification, let's look at a highly abstracted example. Suppose we have two tables, a big table and a small table. There's one copy of the big table in a UK data center and two copies of the smaller table, one each in the US and Japan. And now the computation we want to run is to get both tables into a single data center where they can then be joined locally. Now, how do we run this? We can break the choice that we need to make into two decisions. First, are we going to copy the big table or the small table over the network? Obviously, we want to copy the small table because it is smaller. And then, once we've made that decision, we next need to choose if we're going to copy the small table from the US to the UK or from Japan to the UK. And this choice is much less straightforward because now we need to know precisely what the data transfer costs are along each of those two network links. Again, we had two kinds of choices to make. First, we had to come up with a logical plan saying what operations we were going to run. Were we going to copy the big table or the small table of the network? And then, once we fixed the logical plan, we had to come up with a physical instantiation of the logical plan by choosing how we were going to run it. Which particular data centers were we going to use for each operation? The choice of logical plan was more or less obvious. The cost of the various strategies involved were orders of magnitude apart. But to choose the physical plan, we required much more precise data transfer estimates. And this is essentially the simplification that we make. We simplify the search space by locking down the choice of logical plan very early on based on very simple statistics on each table. And then once we fix the logical plan, we profile it carefully, collecting precise measurements, which are then used to carefully tune the choice of physical plan. I want to stress that this particular division of labor between these two pieces is purely empirical in nature. You can construct theoretical workloads in which the choice of logical plan is much more subtle. But this is something we found to work very well for us in all of our experimental workloads, as we'll see soon. Laid out a bit more fully, this is our optimization architecture. Given a workload, which is a set of queries, we first use traditional SQL query planning techniques to come up with logical plans for each of these queries. And this essentially amounts to picking a task graph for each query. Then we profile these task graphs carefully, collecting precise measurements, which are used by an integer linear program to jointly optimize task scheduling and data replication decisions. And these decisions together comprise the physical plan for the workload. To verify this architecture, we built 3 distinct pieces, one for each of the steps in the process. But because we have limited time today, I will only discuss the second piece, the profiler that collects measurements. Now, what do I mean when I say profiling? Let's take another example. Suppose we have a sales table partitioned across data centers in the US, UK, and Japan. And now we're given this SQL query to process, which asks for the total sales in the electronics category from each city. And we're going to use this natural task decomposition in order to process the query. We'll start by first partially aggregating the portion of the data within each data center, and then we'll merge the partial results centrally in order to compute the final answer. Now, what we want to estimate is how much data transfer there is along each of these edges in the DAG. And these measurements will later be used in the optimizer to make scheduling decisions. Suppose we already have a full-fledged distributed deployment of our system. In this case, getting those measurements is fairly straightforward. We would simply run the task graph as it is on the deployment and passively measure the size of the output at each individual data center. So, relatively simple. But suppose you're currently in a centralized deployment. In particular, suppose you have not yet deployed our distributed execution framework, but are thinking about doing it and want to estimate how much of an improvement you would get if you were to transition away from your current centralized setup. The challenge here is this. In a centralized database, all of the data gets dumped together into this one giant pile, and the distributed structure of the data is lost. What we do in instances like these is to simulate distributed execution on top of the centralized database. We do this by rewriting the task graphs, injecting additional filters into each of these subtasks to restrict their operation to the appropriate piece of the big database. This artificial decomposition allows us to inspect the sizes of the partial results that would have been produced in a distributed setup. We call this technique pseudo-distributed execution. Pseudo-distributed execution is a technique via which we rewrite task graphs to simulate alternative data configurations. What I just discussed was a particularly natural use case for the technique, solving the bootstrapping problem of getting from a initial centralized setup to the first distributed deployment of our system. But really, what this is a fully general what-if analysis engine. It allows the optimizer to try out arbitrary alternative data replication strategies, and even things like adding or decommissioning data centers in response to changes in the load pattern. Now, as for the actual mechanics of how the optimizer employs this technique to come up with the choice of strategy, those are, like I said, too involved to get into in a 20-minute talk, and I will direct you to the paper for those details. And finally, the function-specific optimizations. There's a large body of prior work developing specialized algorithms for various kinds of problems, such as percentile and top k optimizations. We can't incorporate all of these into the core of our system, but we provide an extensible user-defined function interface via which analysts can implement whatever optimizations are appropriate to their particular workloads. As case studies, we implemented 2 particular optimizations from the literature, which, as we'll see, provide significant further improvement over baseline distributed execution. Now let's see how all of this actually plays out in practice. We built a Hadoop stack prototype of our system, which essentially functions as a multi-data center replacement for Apache Hive. And we used it to run experiments at very large scales, testing both a real Microsoft production workload as well as several synthetic benchmarks. This is what we found. We start with BigBench, which is a synthetic benchmark. On the x-axis, we vary the relative data arrival rate, what volume of updates enters the system in between analytics runs. And on the y-axis, we compare total data transfer volumes with centralized execution versus distributed execution with and without caching. First thing to note is that it's not quite as simple as saying distributed execution is always better. If the update rate is very low, or equivalently, if analytics is run very frequently, then the centralized approach actually works out to be slightly better. So that's one of the things that our workload optimizer does. It has the system gracefully fall back to centralized execution if that indeed works out to be the best choice. But the distributed approach does start to pull ahead at higher update rates. At low update rates, there is a lot of redundancy in the query answers for caching to eliminate, so it achieves a significant benefit, but that advantage naturally disappears at higher update rates. And at the largest scale we tested, which was 10 terabytes, the total improvement we saw was a factor of 330x. Moving on to TPC-CH, another synthetic benchmark. Here, we see an even bigger improvement, 360x, and here, caching does very well. Performance with caching is uniformly the best option throughout the entire range. These two were synthetic benchmarks. On a real Microsoft production workload, I can't show you the absolute numbers for confidentiality reasons, but the relative improvement was 257x. And finally, on the Berkeley Big-Data benchmark. Here, if you just look at basic distributed execution, the performance gap is not that impressive, relatively speaking. We only see a 3.5x cost reduction. It turns out that the bulk of the data transfer in this workload comes from a particular top query. And when we implemented the top optimization from the literature, our improvement jumped up by a further 8x to a net 27x improvement. So this shows that our system can function as an extensible substrate via which we can leverage specific optimizations from past work. I've been talking about the SQL model so far. More recently, we've been working on extending to a much more general computation model involving workflows composed out of arbitrary computations. The problem here is significantly harder, but our initial results have been encouraging. We're seeing the same 2 orders of magnitude level of improvement that we were seeing in the SQL setting. And we discuss further details in a paper that we have at Cited this year. There's a large body of related work from various fields, which I don't have the time to get into. But these are the key characteristics which separate us from past work. There's the fact that we support the full relational model at unprecedented scales. There's a focus on bandwidth and the unique challenges that entails. And there's the fact that we can leverage assumptions about the workload to deliver strong optimizations. So to summarize, we built a system to address the growing need for geo-distributed analytics, introduced several novel techniques in the process, and showed that very significant improvements are achievable on a range of workloads. Thank you.
Hi, great work. So one question. So a lot of these data centers, they have one acceleration boxes, right, where they already do redundancy elimination. I wonder if you have looked at, you showed your improvements in terms of redundancy elimination by caching. Mm-hmm. When you have those boxes, how much improvement can you actually get?
So one thing is that all of our data transfers are compressed by default. They are compressed at the application layer. So a substantial amount of the benefit that you would have gotten from a redundancy elimination technique, from a WAN optimization technique, would already have been included in our estimation process. Now that said, I think the kind of caching we do can be viewed as an additional layer of WAN optimization or redundancy elimination in a certain sense. But there are certain semantic aspects to the caching issue, which I didn't have the time to get into, which would make the problem. I mean, there's a layer of optimization involved that just can't be done at the syntactic level that happens in our system.
Okay, great. So I guess no other can ask another question?
Mm-hmm.
So to my understanding, you're kind of doing the query at each individual site, and then you send basically all of them to the coordinator, right? So what if you have some intermediate data centers which are closer to some of these local data centers, but a bit far away from the coordinator? Can you actually do some aggregation, like regionally?
So the two-step kind of process is what happens in only the simplest of our queries. We do joins, for example, which do involve staging in a set of intermediate data centers. Now, in our experiments, we only tested, so all the data centers we tested were holding some amount of data, but I can envision the kind of scenario you are describing, where you can create an additional set of staging data centers which you use to improve data transfer costs. We didn't do that in our experiments, but I can see how that could be interesting. So you could get an even further improvement than the 2 orders of magnitude we are already getting.
Thanks.